So we will talk about wireless LANs, 802.11 that you have used forever, and we will see what are its features, how does the PHY work, how does the MAC work, different things, frame format, power management. So now we are in the networking part of this wireless networking course. Okay, so far we were on the physical layer, which we call wireless communication part of it. All right, so first of all, what is Wi-Fi and what is 11? 11 is a standard. It is done by IEEE. And a standard is actually a big fight where somebody says do A, somebody says do B, and the decision is we'll do both A and B. All right, so there are lots of options. We'll make it optional. If you want to do A, you can do A. If you want to do B, you can do B. So the standards have lots of options. And the problem with that standard then is that if you implement A and they implement B, they can't talk. And that's not IEEE's problem. That is the problem of the vendors who are making the equipment. So what the vendors do is they make their own organization after the standard is done, or during the standard is being done. They make their own organization and somehow they agree more in those organizations and they say, okay, all right, we will both do A. That's it. Nobody will do B. Or there's no harm in doing B, but we will all do A. All right, that way, when you buy the equipment, at least they will work together. Right? So that is called interoperability organization. Interoperability means two vendors can work together. And Wi-Fi is the interoperability organization. It's a group of companies that got together and they named their stamp or trademark Wi-Fi. So if you get an equipment which says Wi-Fi, it is not just 802.11, it is better than 802.11 because it will work with any other Wi-Fi. Understand that difference? So Wi-Fi is the wireless fidelity is a trademark, and it ensures compatibility between the wireless equipment from different manufacturers. And Wi-Fi Alliance, that is the group. Wi-Fi Alliance is a non-profit organization that does the compatibility testing, and you can find about them by wifi.org. You can find about IEEE by going to IEEE.org or IEEE 802.org, things like that, right? But if you want to find out Wi-Fi, you go to this organization. This is different. 802.11 has many options, and it is possible for two equipment not to be incompatible, but Wi-Fi means compatibility. So everybody understand the difference between the two? The normal people outside of this room probably don't know the difference, right? But now that you are a wireless expert, you should know the difference. Everybody understands the difference? Right? Okay? All right. So, 802.11 features. 802.11 was actually done in 1997, 16 years ago. Actually, it was finished in 1997. The work started like 1991. It took 6 years to make the standard with a lot of fights. Because basically what happens is if you have an equipment and you have an equipment, both of you try to make sure that this becomes the standard. Your thing becomes a standard. Right? So there is a lot of basically discussion. It took 6 years in 1997 and it came out at 1 and 2 megabits. That was the best they could do in that time. Right? As soon as it came out, people said it is just too slow. Because we already had 10 megabit Ethernet, and actually we are working on 100 gigabit standards, right? So newer versions at 11 megabytes, right away they started working on the higher speed, and then other versions came out, 11, 54, 108, 2000, and so on and so forth. All versions use license exempt standard spectrum. Now, there are two kinds of spectrum. Licensed spectrum means you are allowed to use it and you are the only one who is allowed to use it, and you pay by $1 billion in that for that one. That is what the cell phone companies do. licensed spectrum. This is license exempt, means you don't need the license, right? Anybody can use it, right? So that's why it is free, that's why it is cheap. That's why you can do as much as you want on Wi-Fi, but you cannot do much on the cell phone, right? Now, a lot of people who are not aware of this will call it unlicensed exempt spectrum. In fact, I went to Wikipedia and they regularly use the word unlicensed, which looks like stealing from somebody, right? If you have a licensed spectrum and you use it, that is unlicensed spectrum, right? License exempt means you are legally using it the right way. So you should understand the difference between unlicensed and license exempt. Now, so we use license exempt. Need ways to share spectrum because it is license exempt, means everybody is going to use it. Microwave people are going to use it. Cell phone people are, well, let's not use cell phone for time being. The cardless phone people are going to use it. Same 2.4. The TV people are going to use it. Anybody who wants to do anything in wireless will use it, and Wi-Fi is one of them. Right? As you will see later on, 15.4 will use it, Bluetooth will use it, everybody uses that same spectrum. And so we need a way, excuse me, are you in this class? Yeah. Okay, so please shut down that phone if you can. Okay, so we need to share, and that is spread spectrum. So we use what? CDMA. That's why we taught you CDMA at that time beforehand, but I could have covered it here too. But basically, CDMA is going to be used in most of the standards that were developed in that time. Remember, I told you that was the best technology you could do in 2000s, right? And so Wi-Fi uses CDMA. Need ways, okay, so spread the spectrum. All right. Then, so there are three physical layers. They use both direct sequence. Now, if you remember direct sequence, right, that is if you use 10-bit code or 15-bit code or 100-bit code, there was direct sequence, spread the spectrum, using ISM bands. I'm going to explain ISM in a minute. And frequency hopping spread the spectrum. And they also use frequency hopping. Right? That was second phi. You could have this phi or that phi. And diffused infrared band. Diffused infrared. So what is infrared? Infrared is just before the red light. So this is, and if you have used any remote control which has a red color, this one has a green, but basically if you have a remote control at home for TV, that is most likely infrared. Okay? And so that was one of the things that was very common in those days. If you bought a laptop, it will come with infrared in the back, red color thing, and you just have to align it because it's a light. So light cannot go like that, right? So if you want to print it to a printer, the printers will have a glass thing, and your computer has a glass thing. You have to just align a straight line. Okay? So there were three physical layers at that time. And so the first two usually wireless, and they are ISM band. ISM is instrument scientific, industrial scientific and medical band. I'm going to come to that in a minute. Okay? So all of these physical layers support multiple priorities. So because the bandwidth is so low, 1 megabit and 2 megabit, it's important that you put high priority things first. If the bandwidth was 1 gigabit, you don't care. If the bandwidth is 1 megabit, you really care that you get through your important work first. Right? So supports multiple priorities. Supports time critical and data traffic. So you could even send voice or even video through the time critical things. Okay? And data traffic, of course. Power management allows a node to doze off. And basically, that is one thing which we'll see in all the technologies that we discuss in the wireless, is that they generally run on batteries and power is at a premium, and therefore we need to find ways to reduce the power consumption, and 11 has some ways so that the stations can sleep most of the time. All right. Any question about any of this? Yeah.
Since the spectrum is license exempt, are companies required to share the spectrum, or can they hog it?
They can hog it, but the thing is, I mean, obviously they won't survive for very long in the sense that as soon as you bring that equipment, everything stops working, and then people say, okay, take this out. So you would be just bad reputation.
Also,
Yeah.
the license exempt doesn't mean that there are no regulations for it.
Okay, so license exempt, that's a good question. I mean, basically license exempt means you don't need the license, but there are lots of rules you have to follow. And so if you follow all those rules, then you won't be really hogging much. So there is, for example, limit on the how much power you can put. I mean, you cannot put a microwave and open the door, right? That is a license exempt band, but not at that power. Okay? All right, so ISM band. So there are actually many ISM bands that, now, who gives the license? Basically FCC in the United States, for the United States. Other countries have similar organizations. FCC is the Federal Communications Commission. And so FCC says that, well, you can use this little bandwidth, so on and so forth. And so these are all the things that are available. All right, and every country has their own list. But the problem with these, some of these little ones, is that you have very little bandwidth, 30 kilohertz. So you cannot get too many megabits through that one. So you really start getting something significant once you get into gigahertz. And the higher you go, the more you have. Right? And as you know, with the long one, you cannot really go very far. And therefore, it's not very useful to have these big ones here. So we really settled on the middle. Right, where you have enough spectrum and enough distance coverage. And second thing is, some things are not available everywhere. For example, this particular band may be available in America but not available in Europe. So you don't want to design equipment which you cannot sell there. Right? So everybody concentrated on this one. 2.4. And so everything that you are using right now uses 2.4. Well, almost everything. Because 2.4 is now very congested. Yeah.
So when you buy a dual band router, it's using 2.4.
Exactly, that's the point. So now we are trying to move into 5.8 gigahertz. And so that's where a little bit more spectrum is also available, and little bit is more space in the sense that less people are using it. So now when you go to buy even a cardless phone, it comes in two bands, either 2.4 or 5.8. When you buy Wi-Fi, obviously it comes in two bands. So everybody is now getting into 5.8 slowly. Yeah.
I guess why 5.8 is not 5.725?
Wi-Fi is?
Why do people use 5.8 instead of like 5.
Why they call it, okay, they call it 2.4 and they call it 5.8?
No, why do people use 5.8 instead of like 5.85, for example?
Okay, I think if you're asking that why don't they use in the middle, I mean, if some other number? Yeah, that will come in a minute. Okay. Yeah, but this is the whole band is available. This much is available. You don't have to use the whole thing. You can use just a little bit. And we will see that in a minute. But the idea is that these are all different bands, and there are many other bands for license use. And every band has a name for it, and every band has a license, whatever it is used for. For military, for radio stations, television stations. We saw that spectrum, remember? So this is license exempt. And this is for your scientific, medical, and industrial use. And and you can see, obviously, the lower is better in terms of distance, higher is better in terms of bandwidth. It's very easy to get 2 gigahertz when you are at 244 gigahertz. It's very difficult to get 2 gigahertz when you are at 6 megahertz. Right? So that is as simple as that. All right, so we all use ISM now. ISM, now the question is, how much can you use? So what they did was the ISM band, let's say 2.4 gigahertz, was divided into 12 channels, each of them 20 megahertz wide. So channel 1 goes from this place to plus 20. So it is like 2402 to let's say 2422. Now the problem is the channel 2 starts right 5 megahertz behind it. So channel 2 will start from 2407 and go up to 27. And channel 3 and 4 and 5 and 6 up to 11 and 12. So if I use channel 1 and use channel 2, we are going to really collide. They overlap too much. And therefore there are only 3 channels, even though there are 12 channels for the namesake, there are only 3 non-overlapping channels. Channel 1, 6 and 11. Okay? And so this is what you use. Have you ever programmed your wireless router? And it gives you only 3 choices. 1, 6 or 11. How come there is no 5, 4, 3, 2? Because it just is not, good. Those are not good channels. You have a question? You have a question? No, okay. All right. Similarly, on 5 gigahertz band, there are many channels, and you can count how many you could have, lot many more, in terms of, if you just divide by, 5 megahertz, but only 12 non-overlapping channels. All right. So if you program for this, then you will have the choice of 36, 44, 40, 40, and blah, 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 and so on and so forth. All right. I have programmed lots of wireless routers, but I have never had to worry about this part because there is so much here that right now you don't have to select anything. The router just knows how to select, something. And so nowadays they're coming up with automatically sensing the area, finding out what is the use and what is the right channel to use. So that's why you don't have to remember these numbers, but 1, 6 and 11 I have to remember because somehow if you have an old router, it is fixed and you have to change it manually. The new routers, they do it smartly. They just figure it out what is the right one. If you put 2 of them together in one place, one will take 1, one will take 6 or 11, because they will just figure it out. Yeah.
Because 14 times 5 is only 17. Why they design it like that into an overlapping channel?
Why did they design overlapping channels? Yeah, I don't know about that part. Sorry about that. I don't know why the channels were numbered like that, where they had 5 megahertz really non-overlapping and then rest was overlapping with the next channel. So that was before my time. But so I don't know the answer to that question.
But to provide higher data rates, because we were talking about up to 108, they combine all these together.
Okay, so we will come to that in a minute. But generally you are supposed to use one channel, not all 3. And although there is no law against it, if you use channel 1 and 6 at the same time, they won't come and catch you. But being a good citizen, you just use one channel. Okay? Now there is a law against using too much power. So if you were using channel 1 and using power there, they could come and catch you. So FCC does have a police. So basically, the radio spectrum is monitored, and anybody is not following the law, they could just say, look, this is misuse and all that. So that is, but there is no law against using 2 channels. Yeah.
5 megahertz has a shorter distance.
5 is shorter distance too, yeah.
But how much, I guess?
Yeah, we'll come to that when we understand. But basically, right now you can use by d raised to minus 4 law, and then you know that. Well, that is this. No, sorry. So you have to go to one of those short distance law where there was a lambda in the formula, and the formula I think it was lambda square. Right. So that will give you the answer. Yeah.
In the future, do you foresee more channels or some type of channel hopping system when everything is connected to the internet? You're going to have all these people.
Exactly. That's what is happening. So that is what is happening. That's why we are moving to 60 gigahertz. Right? We were on 2.4 most of the time. Now we are moving to 5.8. Now 5.8 is kind of a standard. You cannot buy a router without 5.8 today. Right? Tomorrow when you go to the market, it will be 60 gigahertz as well. Now 60 gigahertz, as you can see by this formula of lambda square, will not go very far. All right? So that is going to be used for connecting your TV to your DVR, which is right in the same room. In the same rack, maybe even. Yes, so we are moving upwards. All right. Now, a little bit more about the physical layers. We already said most of it, but 802.11 used 3 physical layers, 2 in 2.4 and 1 infrared, no longer used. But then they started working right away on the extensions. Now, before I go into the extensions, I just want to explain to you how the IEEE standards are numbered. So they started working on two or three different standards. First of them was called 802.11a and another one called 11b. So this work started basically right when 11 was finished. So like they started in 1997. They said, oh, this is not good, we need to go higher speed. However, so basically the way standards are numbered is that you have 802, which is when the Ethernet work started, February of 1980. So that was the committee. That is when the IEEE started making standards. Okay, and then they had numbers of different standards. So 3 was Ethernet, 4 was some bus, token bus, 5 was token ring, and so on and so forth. By the time we came to wireless, it was 11. Okay, now they are up to 22, 23. WiMAX is 16, and so on and so forth. So they're, the numbers are increasing. And then when they have an amendment to the standard, amendment means just a small change to the standard, they'll put a little letter behind it. So A, B, C, D, E, F, G, all the way to Z, Z, and then they start A, A, B, A, C, A, D. So right now we are in 802.11, I have a list in the next lecture. I think we are somewhere on A, F, or A, G, A, H, something like that. Okay, so we finished 26 amendments from A through Z, and then from AA through AI or something. All right, so that is second thing. And then there is, of course, a year when it was finished. Now, the idea is that these standards you cannot find anymore. If you go and look for an IEEE website for 11A.99, it is gone because it is an amendment. Right? So whenever they get time, they just take the amendments and put into the base standard and issue a new base standard. So if you want to find 11A, you have to go to 11. Right now it is 11-2012. So a new standard for 802.11 came last 2012, and that has all the amendments up to that point. All right, so you will not find A through Z, most of them. You understand the now numbering? Right? So I will give you the original standards, amendment, date, and all that, so that you know when it was done. But these are all now part of the standard 11. Okay? So that one said we will work in 5 gigahertz band and we will give you 54 megabits per second using 20 megahertz OFDM. Okay? And the B also started at almost the same time, and they were less ambitious. They said, we will give you 11 megabits without going to FDM. We will give you 11 megabits in the same in 2.4 gigahertz band using 20 megahertz. Okay, this is just a QAM kind of thing. Okay, so this actually came out first, and most of you didn't really see, or if you were watching for it in those days, which most of you probably were not. But 11B is what came out first and was productized first, and most of us have it. 11A came out later, and it came out later for two reasons. First of all, it's the wrong frequency, 5 gigahertz. Nobody wanted to get into that band, right? And second thing, OFDM probably was more expensive in those days, new technology. So G actually came out the standard came out. So basically what happened was, as soon as this came out, they started working on another version of 54 megabits without going to 5 gigahertz. So they started working on G, which was using 2.4 gigahertz and giving you 54 megabits for the same frequency using OFDM. So they didn't want to change the band, because a new band requires new all analog circuitry and all that, right, which is kind of expensive. So 2.4, so this one actually, B and G became more famous than A, more popular than A. Most of you have B and G first, and then now we are getting A as well. So now we get A, B, G. Actually, today we get A, B, G, N. Okay, any question about this? Why the things are numbered that way, and why they came out in the wrong order? Yeah.
I guess what happened to, it says the Fourth Amendment was G, but what happened to...
No, there is more. So there is A, B, C, D, E, F, G.
Okay.
There is a whole thing. I mean, I have a list someplace later on in the next lecture. But the thing is, some amendments have nothing to do with the speed. Some amendments just have to do with management, or something else, which is here we are talking about different speeds. Now, before I go into the how do we share the medium on wireless, you all have read Ethernet, and Ethernet we use CSMA CD. CSMA CD is carrier sense CS, MA multiple access, carrier sense multiple access collision detection. So what you do is you sense the carrier, you listen. If somebody else is speaking, you don't start. Carrier sense, right? And collision detection. If you start speaking and somebody else starts speaking at the same time, because nobody was speaking before, now you are there and I am here, so at some point your voice will come to me, few microseconds later. Then I will stop. So collision detection means you keep listening while speaking. Okay? That is what Ethernet does. CSMA-CD. Here we cannot do that. Why we cannot do that? Because of the hidden node problem. What is the hidden node problem? Is that we may not even be able to listen to you even though we collide. So here's the example. C is trying to talk to B and A is trying to talk to B. They are both talking at the same time, but they cannot listen to each other. They might continue talking for hours, but they not listen to each other. So they will not be able to detect the collision, even though they are both colliding at B. Okay? So what we need to do is we use what we call CSMA-CA. Carrier sense multiple access with collision avoidance, not detection. We cannot detect it, but we can avoid it by doing some more work. And we need to do four-way handshake. So if you want to talk, you say to access point, I want to talk. And everybody else says to access point, I want to talk. Then the access point says to one person, okay, your turn. So clear to send. Everybody listens it, because everybody can, here's the interesting thing. Everybody can, if they are talking to access point, if they are in the same area, they will all be able to listen to him. They will not be able to listen to each other. Basically to it. Let me put it this way: they will be able to listen to access point and talk to access point, but they will not be able to talk to each other. So here, ready to send, clear to send. So one of them will get clear to send. If suppose too many people say, the access point may not listen to anybody, and nobody will get cleared, and they will all say again next time, sorry, I want to talk, right? So hopefully they will not collide. Now, once somebody gets the clear to send, everybody listens to that you are clear to send. Basically, you don't only say, I'm ready to send, you say, well, I want to talk for 11 seconds, or 11 milliseconds, or microseconds. And the station says, yep, you go ahead and talk for 11 microseconds. Everybody listens, and everybody now quiets down for 11 microseconds. Right? Then this station goes ahead, sends the data, gets the acknowledgement, and now it's done. Now we start all over again. So to just send one message, we send 4 messages. On Ethernet, this would have been one message, because we don't have any acknowledgement on Ethernet. And we don't have CTS and RTS. This is RTS, this is CTS. We don't have RTS, CTS on the Ethernet. You just speak. Okay? So we do 4 times that work. Now, first of all, why do we need acknowledgement? Yeah.
So everyone else can hear the acknowledgement and know that the transfer is over.
That is one thing, that everybody can hear that the data is done, but that they could have done if they wanted the CTS. They would just know, right? Yeah.
Share data transfer?
Because there is a lot of probability of error here. There is a big probability of error. In wireless, in wired networks, there is probability is 10 raised to minus 12. When we designed Ethernet, by the way, I was involved in the design of the Ethernet 1980. I was involved in all of these standards. So those days we put the bit error rate for Ethernet design 10 raised to minus 12. You can't even imagine that, right? In wireless, it is more like 10 raised to minus 3, 4, 5, something like that. It is just several orders of magnitude high. So since even though you got the time, and even though you are not, nobody else is transmitting, there is no interference, but there is noise. Right? So it is quite possible that this guy didn't get it. So when somebody gets it, they check the CRC. If the CRC is okay, then they send the acknowledgement. Okay, so you need all of these 4 messages. So the MAC, the media access control for 11 is CSMA, CA. Listen before you talk, that is CS. If the medium is busy, you back off. Avoid collision by sensing a short message, and you do send the RTS. RTS contains the destination address, duration of the message, and tells everyone that I want to talk for this long, right? And CTS, you get the CTS. And the stations actually have a vector which says when they can talk. So they just update that vector saying that, okay, all right, I am not allowed right now. So so actually it says cannot detect collision, and therefore each packet is agged. I should say that because of the noise, each packet is agged, and MAC level retransmission if not agged. So that's another thing. If you don't get the last ACK, this will send another RTS, CTS stuff. Alright, on Ethernet we don't do that. On Ethernet, if it doesn't get through, let TCP worry about it. Right? Here, TCP of course worries about it, but we want to make sure that TCP doesn't have to worry on every packet. Alright, so we have 2 transmissions, layer 4 and layer 2. All right, any question about this MAC? If not, then we go into a little bit more detail. So basically, if the medium is busy, when it becomes available, people don't just start transmitting, they have to wait for a certain amount of time. And the amount of time they have to wait depends upon what they want to transmit. So there is a short interframe spacing, CIFS, which is the most highest priority thing that goes out at that delay. Then there is a PIFS, which is medium, and there is a DIFS, which is larger. If nothing happens, if nobody wants to send up to this point, if the medium still remains available, then we do what we call a contention window. That is where the CSMA CA starts in that sense. Carrier sense is happening all the way here, but here where you will send your RTS, etc., your things which will basically get you onto the wire, or get you onto the medium. Now, so let's start with this. IFS stands for interframe spacing. I shouldn't say initial. I think I should remove the word initial. Interframe spacing is IFS. So highest priority frames are sent with short IFS, CIFS. Highest priority frames. And what is highest priority? ACKs. If somebody has just finished transmitting, we want to make sure that they get the ACK, because they just used the 11 microsecond. We don't want to waste that 11 microsecond. We want them to get the ACK right away. So that is CIFS. Medium priority time critical frame use point coordination function. I will explain that point coordination function in a minute. So PCF. This PCF uses PIFs. And there is a DCF, distributed coordination function. They use DIFs. So you can see these are medium priority. This is high. This is lowest priority. This is the highest priority. So how does it become? Basically what happens is the whole time is divided into super frames. Super frame means a fixed duration, 2 milliseconds, 5 milliseconds, something like that, right? So every beginning of the super frame, the access point sends out a beacon, sends out an announcement which says, look, I am here, I am for Bristol encrypted number 1.0, 2.0, and there are lots of other things in that beacon. Okay? So that beacon is the starting point. After that, some time is automatically reserved, and actually it will be announced in the beacon how much is reserved for PCF, point coordination function. Okay? Now, point coordination function is something that you don't contend for. So, suppose you are transmitting video. Now, you know that for the next 1 hour, you will need 1 megabit per second. Right? So, you could tell the access point, look, I need it every super frame, I need 10 microseconds. Right? And you will be allocated that, and that is guaranteed reserved for you. So that is what is called point coordination function. That is something that is repeated every frame, for some time. Okay? So PCF. After the PCF, now PCF may be 0, which might be most of the time, because if you're not really doing video on wireless, you might just be into DCF. DCF is distributed coordination function, and that basically means that, here the reason for it is called PCF, is because one point, the access point, coordinates it. Right? DCF is distributed coordination function, is that everybody that basically is now trying to get to it. All the access point will be the final one which will say who can do it. But really, you just collide and try to do it, right away yourself, right? So this is DCF. This is the contention period. This is contention free period. There is no contention here. It's already guaranteed given. You don't have to wait anything. When your turn comes, you just go. So time critical services use PCF. The point coordinator allows only one station to access. Coordinator sends a beacon frame to all stations, then uses a polling frame to allow a particular station to have a contention-free access. Contention-free period varies with the load. So this is all basically, you just tell them, and then, they will tell you that, okay, you have so much time, and at this point your thing begins, at this point your thing ends. So this is all pre-allocated. DCF is much more complicated. DCF is much more complicated. So what happens is that for DCF now there is no priority actually. Once you are in DCF, you just stand behind in your station in a queue, and each station keeps three variables: a contention window, a backoff count, and a network allocation vector. Okay. Now, if RTS CPS is heard, then the nav is set to duration in that frame. So if suppose you hear somebody says, I want to transmit for 11 microsecond, then you said that, okay, I won't worry about anything for the next 11 microsecond. Actually, if somebody is cleared to send for 11 microsecond, then you know that that is the one, right? Not for RTS, CTS. You look at the CTS and you say, well, now this guy is going to do for 11 microsecond. I shouldn't even try anything. So you just set your next sensing point at 11 microsecond from now. If the medium is idle for diffs, now if your nav is expired, then you see if it is nobody has used it for diffs, then backoff is not already active, then you draw a random number between 0 and CW is the congestion window and sets the backoff timer. So you somehow draw a random number just like Ethernet. You draw a random number and you say, well, I'm going to wait for this long. So if 5 people want to transmit, they will all draw a different random number. Somebody will come up with 1, somebody will come up with 3, somebody will come up with 5. So you have to wait for that long. And hopefully everybody is truthful in the sense that not everybody, that you could program a station so it always draws 1. Right? You will beat the system. But hopefully you have not done that, and so you will draw a different number. So whose timer expires first will transmit. Okay? Clear? Now I will have an example in a minute, so that will make it more clear, and this is homework too, so this is clear. This has to be clarified. Anyway, the congestion window, when you draw the random number, actually is minimum. You start with the minimum. After each successful transmitter, you set it to minimum, but after each unsuccessful attempt, you increase it by 2. So you did 2 CW, whatever the value was, plus 1. So if you are 1, then you make it 3, comma Cmax, and you don't go over certain value. In case of Ethernet, Cmax was 10. Right? So you started with some. Well, actually, there actually was slightly different. Sorry, Cmax was not 10. It was 2 raised to 10. So in the case of Ethernet, it was 2 raised to 10 is the maximum backoff. Here, you go by factor of 2 all the way up to Cmax, which is some value which is set up, right? So you double the backoff. So that way, if there are too many stations, they will draw out bigger numbers. Okay? More widely distributed numbers. Here are the typical values. Now I have used the word U for mu, micro. So the slot time is 20 microseconds. So everything is counted in the units of 20 microseconds. Actually, this is what you use multiple for transmitters for your data. Fifths is 10 microseconds. CW min is 31 to 1023. CW min is 31 and CW max is 1023. So what you will do is you will set your congestion window first at 31 times slot time, which is 20 microsecond. And then maximum it will be 1023 times the slot time. So slot time is the unit of time. It just happens that the CIF here is half of the unit of time. So this is for DS phi, for FH phi, frequency hopping phi, 50 microsecond, CIF is 28 microsecond, CW min is 15, and so on and so forth. Now, I don't think you will remember any of these numbers, and you don't have to remember any of these numbers, but each of these, A, B, G, they have specified some default values. Okay? But in our exam and in our homework, we will give you the values, and then you have to know how to use them. So here is an example. slot time is 1, CW min is 5, diffs is 3, piffs is 2, cifs is 1. Okay? Now, what you should do is you should look at this slide, next one, and this picture together. I can't do that. So I'm going to explain using the picture, and you can read this next slide as well. So really what is happening is that this is the access point, this is station 2, 3 and 4. Now at this point station 2 suddenly gets a frame to transmit. It has a desire to transmit. S3 gets the desire to transmit. S4 gets the desire to transmit. However, the access point is transmitting the data already. So the medium is busy. Right? So all three stations wait until the medium becomes available. At this point, everybody is waiting to see how long it remains available, but the frame was sent to 4, from the access point to 4, and therefore the first thing 4 has to do is to send the acknowledgement. Right? So it will wait for this shortest time, CIFS, 1 interval. Right? And it will send the acknowledgement. That will get through. Nobody can do anything in there. So now these guys say, okay, all right, now everything is, well, let's wait. And now they wait for, and nothing happens for 3 units. Now this is means, now we are into the distributed function area, contention area. Now we can contend. So they draw their random numbers. This station drew a random number which turned out to be 2. This one drew a random number which turned out to be 3, and this one drew a random number which turned out to be 1. Okay? The CW min is 5, so they will draw a random number between 0 and 5, and this is the number they got, 1, 3 and 5. Okay? Since this got 1, it waits for 1 more unit of time and then it starts transmitting the data. Well, actually it cannot transmit the data, it sends an RTS. It tells that I'm ready to transmit. Okay? It sends an RTS to the access point, and then 1 unit later it gets a clear to send. CTS. Right? Nothing can come in between, because after the RTS is done, you have to wait 1 unit of time before anything can come, and the highest priority things are RTS, CTS and acknowledgement. Right? So the CTS comes through. Now everybody hears the CTS, and CTS says, well, I'm going to transmit for whatever length here. And so actually it says in your slide that it says that I'm going to use it for 8 units of time. 8 units of times includes RTS, CIFS, CTS, CIFS, data, CIFS, acknowledgement. All of that time is now given to this station. Right? So they change their now timer so that they will wait for 8 unit of time. Anyway, so this station which has gotten the CTS will send the data, which happens to be 2 units of time. Then it will wait for the acknowledgement, which comes after 1 break and then 1 unit of time. Right? And then we are ready for, nothing happens for diffs, 3 periods, so now they start. Now the thing is, here is the thing. You don't draw the random number again. You already drew the random number. You were unlucky to have drawn 3 or 2 or whatever. So you start. So basically, you keep your backoff timer where it was. Right. So where it was. So when this guy had drawn 3, and they were counting. This guy had drawn 1. They were counting, and this guy was drawing 2. They were counting, and suddenly this guy's timer expired, and it says RTS. At that point, this one stopped counting, and it had 2 and this had 1. right? So they will now count to that value. So this will count to 2 and this will count to 1. This will expire first, right? So this will send RTS. Ready to send, and it will get the CTS and data and through, and then at this point when this acknowledgement comes, what will happen after this acknowledgement?
S2 will get brought on.
Yeah, then this Y will get the opportunity. It will have to wait for 1 unit of time, and hopefully nobody else has gotten new traffic and will get through. Okay? Can you do this? If you cannot right now ask, I mean, it's no problem asking if you want a link clarification as to what happens, but this is the homework. To draw a diagram like this. This will be in the exam, to draw a diagram like this. Yeah.
I do have a question, but it isn't quite about this. It's about the nav.
Yeah.
So it would not set it if it's on RTS, correct?
Yeah, right. So I said that you should not set the nav at RTS because really you don't know, because there will more than one RTS quite possible, and I don't know how they will get through. I mean, it is possible that I hear an RTS but you don't hear the RTS, or the access point doesn't hear the RTS. And so I really think that the CTS is more better place, right, for you to guarantee. So when I said CTS, actually that was my view. Now I will have to go back to the standard and check where exactly they do it. Okay, and that's fine toothing to a 1200 page standard, which is really difficult, but we can do that. But basically, I really think the CTS is the one when you really know that something got through, but really the standard says and the book says RTS. Yeah.
So what if during the transmission, if there's another device that joining the...
Yeah, right. So let's say S1 or somebody else gets what they will do is they will wait until here, and then after, see, the thing is, everybody resets their congestion window only after a successful transmission, right? So basically, so this one will not reset it until it gets transmission successful. So it is quite possible that which was the first station, let's say the access point itself, or maybe after that was S3. Okay, S3 may get a data and it had a successful transmission, right? So it will reset its window to 5 Cmin, right? So it will draw a random number between 0 and 5 and contend with everybody else. If it is somebody else, let's say S2, it still has its timer going, so it will not touch its timer.
I mean, what if there is a F5 joining?
Yeah, so it will start at 5. I mean, if you start with minimum. Once you draw a random number, until you have used it, you don't draw another one. Is that clear? I mean, like,
the new device don't know if there is something...
there are 2,000 people waiting, yeah. Your new device doesn't know, and other people have already tried 5 times and their timer is so big, and new device comes in, can start at 5, yeah. Does that answer your question? It's not a very satisfactory answer, but that's the way it is, right? The new device has no state. It doesn't know where the world is. All right. So with that, we will move on to the next issue, which is how the stations are organized. So there are access points in every building or every room. There are lots of stations in that room, and that is called a basic service set, BSS. And this area is called BSA. So this room is a BSA, one BSA, BSS. There is a next room, which is another basic set, BSS. They're all connected to Ethernet in the ceiling by wire, access point. And so this is called an extended service set, ESS. They're all part of the same Boostel encrypted 2.0, right? Where they are in different rooms connected by wire. In addition, there are some stations which are not connected to the access point. They are talking to other stations without going to the access point, and they are called ad hoc. So there are two kinds of stations. One which go through the access point, which is infrastructure, and one which do not go through the access point. They are called ad hoc. And so, for example, I have two laptops here, and if I wanted to connect to them, and I was in the middle of the field, nowhere near the ocean, someplace, I could just talk. They could talk to each other without the access point in the ad hoc mode. Okay, and they will do the same things. They will just have, these SIFs, PIFs, DIFs, everything else, and they will send some beacons to each other and things like that, right? So the idea is there is this ad hoc mode which most of us have not used, but if you try, you can use it. Okay, once in a while when I get stuck in a hotel where I need to transfer something from to there are two choices. Either I can use USB flash or I can just use wireless. Okay? All right, so now you know what is BSA, Basic Service Area, Basic Service Set, distribution system. This is the distribution system. This is the wire. All right, extended service area is the whole thing. Extended service set is the whole thing. And then IBSS is the ad hoc part. IBSS is independent basic service set. And so this is the IBSS. IBSS. Now the frames. 802.11 frames look very different from Ethernet frames. Ethernet frames simply have destination address, source address, and some protocol type field. Here there is a lot more. They have frame control which is 16-bit long. Then they have a duration ID. This is how long it is. Then they have 4 addresses, address 1, address 2, address 3, address 4. In between they have a sequence control, and then they have N5 and CRC. N5 is basically the data. All right. The frame control itself consists of 16 bits which are used as follows. First is the protocol version. So 00 would be the initial version, and then ABCD will not have a different version because ABGN, they probably use the same MAC frame format. So this is the frame format version, not the PHY version. And then protocol type, the frame type and this frame subtype. And so I'm going to explain that in a minute. 2DS, distribution system, are coming from distribution systems. More fragments, retry, this is a retransmission, power management, and more data, and WEP and so. Let's go one by one on these. Type could be 3 types. It could be a control frame, a management frame, or a data frame. Now, everybody should know what is control and what is data and what is management. Anybody know the difference between management and control? Somebody took the previous class, they should know at least what is management and what is control. You guys just forgot now? In SDN, in OpenFlow, we had management and control, right? Control and data plane separation. So if you don't remember, then it's very short lived memory. But anyway, let me explain. Basically, to do the networks, we need the user sends something which is called the data, right? But there is more on the wire than the data, such as CTS, acknowledgement. These things are not sent by the user. They were created by the station to be able to send the user's data. Those are called control. And they are required because without the acknowledgement, the data will not get through. Without the RTS, CTS, the data will not get through. So all of that is control. Management, on the other hand, is optional stuff that actually you can live without, but we generally use it. Say, for example, I wanted to know how many frames did you get, how many frames were in error, how many frames were collided, and all that. All that statistics has to be collected so that we can maybe put another access point or do something. That is all management, and you can live without the manager. So this is what happens in an organization, in a company. There are managers whose job is simply to figure out if you are sick or not, and if you are sick, to find. But if the manager is not there, companies still work. So management is optional. All right? It is required for good operation. It is required for good performance. So that if everybody becomes sick and there is no management, there is nothing happens, right? So in extreme cases, yes. But control is required continuously. Right? So everything that we have seen so far is control. Right? We saw the packet which is data, which is basically one kind, which is data. Right? So the three types: control, management, or data. Subtype. If it is a control, it could be association, dissociation, reassociation, probe, authentication, deauthentication, CTS, RTS, and ACK, etc., etc. So what is association? Association is when you want to join the network. Right? So you say, I want to join Wustel encrypted 2. You click on that connect. Then, there is some exchange takes place. Right? Association. Reassociation, I want to come back. Probe. Probe is what the station send out. Is there a Wustel encrypted 2.0 here? So there are two ways to find an access point. One is that you sit down and just do nothing, listen to what is being announced. So the access point will announce every beacon. They will announce that I am Wustel encrypted 2.0. I am Wustel guest. I am this and that, right? And then you can just join whichever you want. But another way is that you could ask that I want Wustel 2.0. Are you here? That is a probe. Now why is probe necessary? Because for security reasons, some networks will not announce that they are there. Right? But if you want to find out, then you send a probe and then they will answer, yes, I am here, and then you connect. So you can do that in your home too. You can design, you can go to the router and say, do not announce. And then you go to your computer and say probe. So there is an option in your Windows, if you look, it says connect to this network even if not announced or something like that. Okay? So that is what the probe is all about. Authentication and deauthentication is that password stuff. Right? CTS, RTS, ACK, etc., etc. Retry is retransmission. So this says now this is a retransmission of the previous one. Power management is that basically that, look, I am going to sleep. And the access point knows who is sleeping, because if the frame comes to that station, it will save it and it will announce in the beacon that I have a frame for you. Right? And then the station, if it is awake, the thing is, first of all, when the stations go to sleep, they say, well, I am going to sleep and I will wake up after 8 hours. Actually 8 milliseconds maybe. So I will wake up after such time, and then at that time the station will the beacon will be announced, and then you will get matched, and you will say, okay, all right, I am awake now, give me my frame. All right, so that is the power management. More data. And then when the access point gives you that your first frame, it says, look, hold on, don't go to sleep, I have one more. So these bits are all there in the frame itself. And then WEP is another security thing, privacy. WEP stands for wireless equivalent privacy. Okay? So what happened was, first there was no privacy, there was no security in wireless, and then people very soon figured out that really wireless is the one that needs more security than anything else. And so they put this WEP, which you don't use anymore because now we have some higher level security stuff, much more secure stuff, but that WEP has to do with the security part, and if this bit is set, then there is some information somewhere in the frame. Alright, and the next one bit is reserved. So anyway, so this is all in the 16 bits frame control. Then comes duration ID, which is easy to understand because duration ID says that I am so long. Okay? Then address 1, 2, 3, 4 and sequence control. So let's go through that. Duration ID could also be connection ID. So I should probably change this to duration/connection ID. Okay? If you use the duration field indicates the time in microseconds, and and then the connection identifier is the basically if it is part of that what do you call PIFs stuff, point control. Now sequence control. Sequence control is basically a fragment number. 4-bit fragment number and 12-bit sequence number. So this is frame number 5 and then fragment number 3 of frame number 5. So they divide that 16-bit wheel into two parts, 4-bit and 12-bit. Addresses. There are 4 addresses in the frame. So why do we need 4 addresses? So basically there are 4 possibilities. First of all, the possibility is that it is going neither to DS and nor from DS, so 0, 0, or it is going to DS or from DS to DS or to and from DS. So let's just see first of all. One possibility is that it is not going to DS at all. So it is going from here to there. This is number 1, little one here written down, right? This is the possibility when you are going from this source to that destination directly on the wireless. In that case, your first address would be destination address, second address would be source address, third address would be your BSS ID. So the basic service set ID. So each service set, like this room is a basic service set, a basic service area. It has an ID, and generally ID is the MAC address of the access point. Okay, so this is also 48-bit long. So this will say, well, on this network I want to go from destination to source, and the fourth is blank. Then if it is coming from distribution system, when it is coming from distribution system, so suppose this server wants to send it to this destination. So this is number 2. Right? In this case, this frame is on the air, but it is coming from the DS, distribution system. In that case, the destination address would be in the address field, BSS ID, which is the access point's ID, would be here, and this real source address would be here. So you would know that it didn't come really from access point, it really came from that server. By the way, all of them have the same 48-bit Ethernet kind of address. That is called IEEE 802 address, not 802.3 address. 802.3, 4, 5, 11, 16, they all use the same address format. Okay, so this, even though this is not wireless station, this has an Ethernet address which is 48-bit long. This is a wireless station, it has a Wi-Fi address which is 48-bit long, but they have the same format. They can talk to each other. So that address goes here. And now let's see, 10 is number 3 possibility. 3 is that it is going to the server from this station to the server. So it will be the destination, it will be BSS ID in the first field and the source address right here, and the destination address for the server will be here. Okay? And the fourth possibility is that it is coming from and going to the distribution system. So let's see number 4. Number 4 is like this actually. So there is a repeater. So you are going to the repeater and the repeater is going to send to the destination. So this is another wireless station here. So this is not the final point, this is just the intermediate point, and therefore you put the receiver's address, which is the repeater's address here, transmitter address, which is the source address here, the destination address, which is here, and then the source address, which is here, right? Now there are 2 hops here. Number 4 goes through 2 hops. In the second hop, it will go from repeater to the destination, and therefore the first address would be destination address here, right? This one. The second address, transmitter address, would be repeater's address. And the destination address would be the final destination, and the source address would be the initial source. So these two addresses are saved on the way, so that you know where really the frame came from and where it is really going. And this is just one hop here. That's why you need 4 addresses to begin with for this possibility, where a wireless station could send it to another wireless station. Okay, I think I'm just 2 slides short. Let me see if I can finish this fast. Okay, so the power management is very easy. I think I have already talked about that. Every station, basically, when they go to sleep, they tell the access point that, look, I'm going to sleep and I'm going to wake up at this time. And then the access point basically announces in every beacon whose packets it has, and then when the station wakes up, it looks for the beacon, listens to the beacon. If there's nothing, it goes back to sleep. That's the whole summary of the power management. That brings us to the end of this lecture. So what we learned is 4 key points. First is that it uses frequency hopping direct spectrum sequence, both of the CDMA as well as OFDM. There are many different PHYs, and it allows both ad hoc and infrastructure, and then that it uses SIFs, PIFs, and DIFs. So now you know what is SIFs, PIFs, and DIFs, and that's the homework. Homework is basically to draw that diagram that we did before for this situation which is given here. Okay, I think that's it. And there's a reading list. I hope you read it before you do any of this. Wikipedia links and acronyms.